All right, everyone, welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Monroe Kennedy III, an assistant professor at Stanford and director of the Assistive Robotics and Manipulation Lab, and a national director of Black in Robotics. Before we get going, please take a moment to hit that subscribe button wherever you're listening to today's show. Monroe, welcome to the podcast.
Thank you so much, Sam, for having me.
I'm super excited to meet you and to dig into our conversation. I think this particular interview has been a long time in the works. You were recommended to us quite some time back. And I've been looking forward to this conversation. We're going to be talking about your work in robotics, particularly around dexterity and collaborative robotics. But before we do that, I'd love to have you introduce yourself and share a little bit about your background and how you came into the field.
Absolutely, I would love to. I went to my undergrad institution at the University of Maryland, Baltimore County. There, I majored in mechanical engineering and found a lot of love for dynamics and controls. After my education at UMBC, I went to the University of Pennsylvania, where I worked in the GRASP lab with Professor Vijay Kumar and did work on robotic manipulation and computer vision with my co-advisor as well, Professor Costas Stanilidis. After my time there, I worked a little bit in industry before coming to Stanford in the fall of 2019, where I began an assistant professorship here in the mechanical engineering department, and now courtesy in computer science, where I founded the Assistive Robotics and Manipulation Laboratory, where we build collaborative robots designed to work alongside people to accomplish the hard tasks for robotics and people working together.
Nice. And maybe just we can start by having you share a little bit about what those hard tasks are.
Absolutely. I think a perfect way to kind of think about this paradigm is first to think, you know, about all the aspects of robotics and where we've come to date. So if you kind of back up to, the 80s and the 90s, you have these robots that you see in factories that are, helping you to assemble cars and these other big tasks, doing tasks that are really unsafe for people, but very repetitive. So the robots didn't have to really have a good understanding of their environment. They just had to move accurately and precisely. If you kind of fast forward this to the 2000s, early 2000s, you see robots really being used for autonomy. So now they have to be able to sense their environment, understand their place in the environment, and what they should be doing to accomplish a particular task. And this goes from ground robots to aerial vehicles, and then ultimately even multi-robotic systems working together became the space of robotics, the leading edge, the cutting edge. And now we're on this new horizon where we're saying if we have these very capable autonomous systems, can they actually be good teammates for possibly human collaborators? How can they make human life better, safer, and longer through their activities? And so when you specifically think about what these hard tasks might include, you can ask yourself, well, if I had a robot in my home right now, what do I think would potentially be too challenging for them to complete? So many people have Roombas. You can see them driving around and performing vacuuming tasks. Those are pretty straightforward. And you have a dishwasher, right? That's able to clean, your dishes fairly well, but you still have to put the dishes in the dishwasher. You still have to move your furniture around so that and pick things up off the floor so your Roomba doesn't vacuum up the strings in your rug or something. There's still a lot of things that you have to do. You still have to fold your clothes, that would be great for a robot to come along and eventually be able to do. And so those hard things really center around dexterity. And you can imagine if you didn't have hands, if you didn't have fingers, or it was hard to have a sense of touch, it would be very difficult for you to live your daily life. And some people actually suffer from that inability. And so, when you think about what does it take to make a robot useful in a human space, you can take a moment to reflect on how easy it is for you to do what seems like common things with your hands, but still may be a little bit difficult. And getting into why that's difficult is what my lab does.
Awesome. Awesome. You mentioned folding clothes that I remember seeing at CES probably three something. Yeah, actually, I always have to add three pandemic years to any time estimate.
Exactly.
So it's probably more like 6 years ago. Um, the some company demoed their clothes folding robot, and the thing, spent maybe 10 minutes to fold a T-shirt or something like that. And you're looking at it, and you're like, man, that's so easy for us, and yet so hard for this robot. It sounds like uh dexterity and perception around dexterity are is your answer to why it's so hard.
Absolutely, absolutely. And so you could take any one of these scenarios and just really just expand on that. And if you kind of dig in, it's really easy to see how that the role, that dexterity plays in those abilities.
Hmm. Hmm. um yeah, on this thought of kind of why don't we see robots around doing these things, one thing that we do frequently see are these amazing videos from Boston Dynamics about now robots jumping around and doing flips. And I always like to ask folks who are deep in the field, like, you look at these things and they they give the impression that they turn the robot on and say, "Hey, run around this course and do some flips." And when I talk to folks in the know, at least historically, it's always been, yeah, it's really much more tightly choreographed than that. What's your take on kind of what's happening behind the scenes, and how close they are to kind of this autonomous future for those kinds of robots?
That's a fantastic question. And I would have to agree with the consensus that there is a lot of choreography that's going into making these types of demonstrations successful. But kind of thinking about why, right? And what does it take to go from where they are to, a robot that's truly capable to do this reliably, consistently, and can adapt to uncertainty. To kind of frame that, it's good to understand in robotic autonomy, there's three main parts, right? There's the see, the think, and the act. So, seeing is perception. How do you perceive your world? How do you take observation of your space from sensors, be it cameras or touch sensors, and convert whatever raw sensing you have into a state that you can then say, this is what I want to be a particular thing, right? This is a consistent dimension, a consistent representation of the world and myself and what I want that to ultimately become. And then becomes the think, which is the intelligence and the planning, right? Possibly AI that says, how do I take that state representation that I perceived in my world and then figure out what I should do next in order to achieve an objective or a goal? And then is my act or control. How do I take that goal, that objective, my current state, and drive the state that I'm at to my desired state? And so when you look at a system like that, there's, of course, the see, think, act, control loop, but a lot of the perception is internal. So it says, given the robot's motors and joints, what is my current orientation, right? What is my current velocity? And that's well and good if you're in a very manufactured environment that's suited to the task that you're trying to complete. But often, as we know as humans, the real world is uncertain. The ground may not be always perfectly flat. Your foot may trip or catch on a piece of an object. And when that little bit of disturbance happens, right, how do you handle it? So, one way is to say, again, well, I'll just make my internal body more robust and I'll learn to catch myself. And a degree of that is present in the system as it exists. But when you really want to turn this loose on the real world, it has to be able to adapt to the surroundings and account for that and even predict that. And when you reach that point that you understand not only the internal model, right, for your own kinematics and dynamics, but how that fits into the larger world model and how to adapt and predict that, then you'll see these systems become more robust and ubiquitous and able to exist around us even more.
Mm-hmm, hmm. That kind of, I think, speaks to the way the relationship between the field of robotics and the field of AI have kind of co-evolved, and I don't know if merged is too strong a word, but I'd love to hear you reflect on that. I think at some point, a lot of robotics was happening in mechanical engineering departments, and it was very focused on kind of the mechanics of, the physical implementation of robotic arms and things like that. And more and more, it is happening in double E departments and computer science departments, and this idea of autonomy and AI systems providing this ability to react to the environment, I think is kind of the natural trajectory. How is it? How is it? How have you seen it evolve in that field?
I think that's a great overview. And I kind of go back to what I described for students in terms of the whole trajectory in space of robotics. So I think the hardware and construction is still a very important problem. You need these reliable systems to accomplish what you want. So I mentioned dexterity before. One question you might have is, well, how do we make fingers that are similar to humans and can give you the information to extract the state that you want? So there's a really big hardware and sensor creation problem that's still being solved. How do we create an analog to human hands that's truly reliable and robust? That doesn't really exist yet, and at an affordable price. And then once you have that, then it's that see, think, act. But the thing is, right, when you think about the more complex tasks you want to do, or I give you these really fancy sensors that may have computer vision involved, the question becomes, how do you appropriately model that? And I think that's the real trajectory that's brought us to AI now, because if you go back a few decades, a lot of the things we were doing with robots may have been well represented by analytical expressions. But the moment we think about the real world and being robust and reliable in these scenarios, we need to be able to adapt to uncertainty. And if I program my robot and I put it in the real world and I'm trying to model some aspect of the world, that model that I developed when I'm sitting at my computer and programming, if I made it an analytical expression, may not correctly reflect the real world when the robot gets there. And so the beauty of artificial intelligence, machine learning, is it presents a set of fundamental tools that can actually learn models from data. So I can observe the real world. I can see what happens when I take particular action. And then I can adapt. And then, depending on what kind of model I use, I don't even have to maintain a particular structure, which is a sort of prior that I, as the programmer, may have had about the world, conceived about the world. But in reality, when the robot experiences something that was unexpected, that I did not expect, can I prepare the robot to adapt to that uncertainty, to adapt to what it truly experiences? And that is the true power of machine learning, in its ability to take real world data and express that manifold, express that data in a way that adapts to whatever you actually experience.
Yeah, yeah. Let's dig a little bit deeper into the work you're doing around dexterity. How have you kind of built out a research program to push that aspect of the field forward?
When I first got here, I was working with my students, and we wanted to address what we thought were the big problems that were keeping, collaborative robots from being in people's homes. And while there are a lot of problems to solve that are not completely solved yet in terms of locomotion, perception, in terms of vision, and motion and hand dexterity, we believe that one of the key aspects right now, one of the key challenges, is robots' sense of touch. If you look at a lot of what humans are able to do, we rely on our sense of touch to a very large degree. We have mechanoreceptors in our fingers that are able to give us information about pressure, texture, forces, and all of that information goes back to our brain, and we can do very complex, dexterous tasks with that information. And robots don't have that analog yet. And so within dexterity, there's two main trains of thought. One is, can we make fingers, robotic fingers, exactly like humans, where you actually compress the finger and the physical deformation of the finger tip causes some material to flex or bend or stretch, and then that sends an electrical signal to the computer's brain, if you will? Or could we actually use tools like computer vision that could allow us to see through a transparent finger to the surface of touch? And if you can do that, you can actually get very high resolution, and in some cases, resolution that exceeds human dexterity resolution in terms of being able to sense forces and shapes on the surface of a finger. So my lab, we developed a robotic fingertip called DenseTact. It's an optical tactile sensor in the family of these types of sensors. So there's quite a few out there you'll see in this space. What really sets ours apart is we said, well, if you look at a lot of work in this space with these types of optical tactile sensors, these are extremely powerful because they let you see the fingertip and you can actually use that information to potentially plan how you should move your fingers and your joints and even higher level plans of how to do a manipulation task. But when you want to extend that to a new task, if you're going directly from the fingertip images to some complex manipulation task, that's called an end to end method. It's often very hard to transfer that ability from one task to another, even if the tasks are relatively similar. So if I'm opening up a large water bottle versus a tiny water bottle, adapting to something that to us seems extremely similar can be very complex for the robot. So what we want to do is modularize that process. Can I go from the images that are received by my sensor to an interpretable intermediate output or state, which tells me what is the three-dimensional shape that's calibrated over the surface of my sensor? What is the net force on that sensor? And soon, what is the stress vector field over that sensor? And if we can get there, then we can actually leverage 20 years of robotic research that did this type of analysis for point models. We can now apply this to soft fingertips. And with this input, we think that the machine learning models that plan how to do manipulation will be able to do far, far more with this interpretable intermediate modular output.
This work is super interesting. I was reflecting in my last conversation with Ken Goldberg, who introduced us, about when I was a kid. I had this robotic arm from Radio Shack. Who out there remembers Radio Shack? Probably very few. And I built this basically a touch sensor. It's basically like a piece of piezoelectric foam sandwiched between two circuit boards, and I think you would measure the resistance or something like that and translate that to pressure or touch. And for a while, it seemed like we hadn't really gotten a lot further than that basic approach. So when I hear you talk about this idea of optical vision based sensors inside of finger like manipulators, that's super interesting. Then my reaction is, that's crazy though, that's like eyeballs inside of fingers. um, and of course, that's kind of taking the analogy too strict. It's, its vision is just a way of sensing. It doesn't really, it's kind of silly to translate it to eyeballs. And I think this thing that you've described as like this middle layer that translates, this optical sensor input into, I guess, more foundational physical tactile measurements, I guess, or features. I don't know what you would call that. Um, it's kind of the glue between the two.
Absolutely, absolutely. And there's a paper, and I can find the reference quickly, that was really interesting. There was a study, and in this study, they had individuals look at their hand through a camera as they touched their hand to provide some force. And you could see this through a camera. And they were monitoring their brains with like an MRI machine. And so they would, touch your finger, and then the part of your brain, that cortex that gives you information when you receive touch, would fire, right? But this particular study said, well, what if we turn the sensitivity up really, really, really high for the MRI as we're doing this? And then we touch a few times, but then sometimes we show their hand being touched on the video, right, without actually touching their hand. What happens in that part of the brain? And what was really cool was the part of the brain that, fires due to physical touch fired very slightly due to visual observation. Now, albeit that's external, right? You're watching, your hand through the secondary meaning, but even our brains, as we evolved, have learned the importance, right, that vision can play in giving you information about touch. And so we really, with robotics, can take that huge evolutional step that's impossible for humans to take and say, what does it mean to have the power of vision, right, at the contact point?
Yeah, you gave an example of before we started recording of DenseTact that was super interesting. Talk about this experiment you did about or maybe even it's a kind of a goal or benchmark or something, but building a hand that can reach into a bowl of screws. Talk a little bit more about that.
Absolutely. So I have a fantastic team of graduate researchers, and one of my teams is thinking about how we can use our DenseTact sensor to perform a screw sorting task. And we really want to bring this down to a place that has traditionally been hard for robotics to do, which is manipulating objects between single contact points using soft robotics. And so the paradigm is we take our sensor, we reach into a bowl of screws and we scoop up some, and we'll have a bunch of screws in our hand. And we can use the fact that we're using a camera inside of the finger to identify which screws are between our fingers. So we can use our depth and shape sensing to give us information about the head and shaft dimensions of all the screws. And we can use the raw image input and segment that and figure out where the threads are and figure out what the threading of your screws are. And then from that information, classify which screws are in our fingers. Then we can take the next step to say, now that we've done that see think, that perception part, right? Now that we know what's in our fingers, we can plan on a motion because we have these soft fingers. How should we move our two fingers together, roll them on each other, and push them into each other such that we can center the contact point through static rolling friction of our screws and select the ones we want and drop the ones we don't want back into the bowl. And so by doing so, we could say if I have, three screw types, red, blue, and green, if I have two blues, a green, and a red, and I want to sort the blues, I can figure out how I should roll my fingers together and how I should change the internal pressure to select the two blues and drop the green and the red, and then move that over and drop that in their respective bins. And so this is one of our first steps with this DenseTact sensor, really trying to attack those problems that have traditionally been out of the scope of robotic dexterity. And down the line, we'd love to say, well, if you could do that, and you had additional information about forces, what does it mean to think about putting a microchip into a board? Right? What happens when you need to have information, finite information within the contact area of soft robotic fingertips? How can you sense that, detect that stably, reliably, accurately, and then leverage that for control?
Yeah, just to play devil's advocate on that use case, like if I've got this manipulator that can, dig into the bowl and pull out a screw, why can't I just add an 11th camera that looks at the screw and does all the things that you want to do in the visual domain without the tactile domain?
That is a fantastic question. I'm so glad you asked it. So, I think the conception you have in your mind right now of this is that the screw is so large that if you're holding it in your hand, an external camera would be able to see it. But the screws we're dealing with are so small. We're dealing with small screws that are so small that when our fingers push together, you can't see them from the outside.
Got it. And yet you're able to, with these tactile sensors, still resolve thread pitch and all that stuff.
So we treat those as like a pattern that we're able to see on the inside of our image, and then you can perform pattern recognition and recognize your screw thread.
That I think that kind of further supports using visual sensors because the resolution, at that short distance is going to be very high as opposed to like some matrix of physical sensors that you'd never be able to do that with these very small screws.
Absolutely, and that's such a great point because this is the leading challenge. You mentioned that piezo resistive sensor you can have. That's been a very popular method, and if you're trying to manipulate big things, that may work well enough. But as you get smaller and smaller, how do you fit these types of physical transduction sensors closer and closer? And how do you get all the different modalities of sensing at once? So if you think about material, if you had like a blanket, think about like a stretched blanket. I could push into a blanket, and that would give me my normal force. And essentially, your piezoelectric resistive material, when you compress it, you're changing its dimension, and it's sending that electrical signal to your system. But there are other forces you could get. You could push in like this. You could actually cause sliding or shear of the blanket, and you can cause torsion at every single point. And detecting all of those modalities are extremely hard for physical transduction sensors. And what you end up having to do is, for physical transduction, kind of create little scaffolds that allow you to move in every possible way. But that usually becomes big and you lose resolution immediately. And so vision is a really good tool, because if I have a surface, let's say silicone, which is what we use in DenseTact and a lot of similar sensors, if I put a pattern, if I etch a pattern onto the surface of the
I was
sensor,
imagining that you were either printing or etching a pattern into the
stamping for us,
was it the sensor or is it the back of the cover or the fingertip or something like that?
the fingertip itself. So the fingertip itself
That is the
will,
sensor, yeah.
exactly. So we essentially give our fingertips fingerprints, right? So these continuous patterns that are on the surface. And then what you can do with your camera is watch how that pattern is being deformed. So if it's stretching, then maybe you're pushing in or pulling out. If it's rotating, then there's some torsion. If it's sliding, then there's shear. And depending on your calibration method, you may be able to have a calibrated output for up to the per pixel measurement that you're able to see when you're tracking that pattern. And this opens up just a huge domain if you can ultimately reach a stress vector field, a force vector field over that contact area of your sensors.
Mhm. And just kind of looking through the DenseTact paper or one of the DenseTact papers, there's kind of a classical encoder decoder picture showing what I'm imagining is kind of the visual input of this deformed field, and on the output, kind of some of the more traditional sensor measurements that you're looking to deliver.
Absolutely, absolutely. And I think this, thank you for bringing up that point. So, this is actually a perfect example of how AI can play a really big role in solving this sort of mechanical problem. So, if you look at a lot of other papers of this type, right, that are trying to reconstruct a surface shape, the basic inherent principle is you have light inside of your finger, like an LED, that shines and through the transparent medium or clear medium hits the surface and bounces back into the camera. And so, based on the angle of the surface, the intensity of that light when it reflects will change. And you'll find that there's actually a very nice one-to-one mapping between that intensity and the light that's struck and come back into the camera. And you can use that intensity to tell you something about the surface normal at that point. And if you have all of these surface normals from all these light intensities on your fingertip, then you can think about, if I have all these surface normals, if I knew the boundary condition where my finger is attached to the edge of my finger, right? The soft medium is attached to the edge. I have boundary conditions and I can perform an integration to actually give me back the shape, the manifold, right? Just from looking at the intensity of the light.
Yeah. And when you say surface normals, you're just speaking about the direction of that surface at any point, like the vector um, of that surface.
Exactly. If I have a plane and I poke a line through it, if that line doesn't cast a shadow onto that plane at all, then it's normal to that surface, right? And so I can string those all together and integrate them to get this surface normal. But this integration process, our Poisson integration, right, is actually really hard to solve. And if you don't have perfect measurements, your integration won't match because there was a little bit of uncertainty, and so there's a little bit of off-putting. And so similar works, they actually use a lookup table. They say, I have all of these set points, and then I'm just going to bin them to this relative area. And the resolution of their lookup table is the best that they can do. But we realized that we could actually use convolutional neural networks, this autoencoder decoder structure you mentioned, to perform the integration for us. And so we chose the dimension of our network that allows the network to look at this deformed image and correlate it for this sensor. You can then look at that intensity and perform that integration and have the output, which is the calibrated depth sensor. And so the question is, well, how did you get that? How do you get the answer? Because usually when you talk about networks, you have to think about loss functions. So I can pass anything forward through my network, but I have to train it. And that training, right? How do you get that high resolution? Well, almost, which is a great way of thinking, though, right? Because it's still very hard to model, and you're using silicone, so it can actually change over time and everything like that. And there are tools that you can use to kind of simulate that, but it's still not quite perfect. But they're actually under construction. Uh, but what we realized was to get that really high resolution, we tried a few things, and the thing that worked the best was 3D printing a surface. So because our sensors have a hemispherical shape, we could 3D print a dome where there are indentures inside the dome that we know from our CAD model, our designs,
Because that's you designed them
because
there.
we designed them. So now our uncertainty is the uncertainty of the printer, right? How accurate is the printer? So 100 microns. And now I can take my sensor and push it into this known shape and all the configurations. And we do this 30,000 times.
100 microns is not your typical 3D printer, uh, consumer 3D
Yeah,
printer.
so we have a S5 Ultimaker, so it stands about 4 feet off
Okay.
the ground and can do a lot for my lab. So yeah, but there's even printers that can even go beyond that in their certainty. But once you have this and you've collected 30,000 touches, you can train that model, that we showed for the first time.
How many of these 30,000 touches that you've collected, how many are uh, touches of unique shapes? Like how many of these molds did you print?
So for each mold, we would rotate our orientation about I think about 200 times, and so we don't have to print as many of those. So those are in the hundreds, and then for those we rotate as we touch to get the image from different orientations as we touch into that surface. Right.
How kind of analytically grounded was the pattern of things that you printed and the methodology of rotating it? Like, did you design that to achieve certain coverage thresholds or something like that?
Exactly. So we knew that we wanted to have like an impression depth of about 5 millimeters. And we also knew that we needed to have different designs that covered the full space of the image so that you could calibrate that whole sort of area. And usually didn't want to just have one area having some features and others that didn't. You needed to have multiple areas that also provided that information. And so we use these principles to guide our sort of design for coverage, and so that's really how we thought about it, right? What was the range of depths that we wanted to experience, and how do we ensure that we covered the full area of these sensors, so that when we have a holdout set for things that we didn't touch, you could see them quite well. And the litmus test for this is in our first paper. You'll see this video in DenseTact 1 where we take a screw, and we never trained on this screw before. And we push this screw into our sensor. And we show you at the end of this video, if you look at it in high resolution, how you're actually able to see the head and the shaft of this screw, even though that was not in the data set.
That screw or any screw?
Any screw.
Meaning the data set is just these deformations.
Yeah. But you could apply it to this screw case, and then you could compare the point cloud and see that this was in fact accurate, right? And so the resolution of the printer wasn't down to the threads of the screw, but it was down to the point that you could see the shaft and the head of the screw that we chose. And so for a random shape in the domain of the deformation and resolution of our 3D printer shapes, we're able to actually see any shape and have a calibrated depth output.
Yeah, you mentioned that something there that uh, was kind of related to my next question. The domain of these shapes, like, to what degree did you need to, for example, have different textures? Like, if you want to get good at screws, you need to print out ridges. If you want to get I don't know what the other examples would be, but like, ridges and rolling and, sharp points and things like that. Is that a thing for what you're trying to do?
Absolutely, absolutely. And so in these points that actually deformed, we were able to print a lot of these different types of features that you mentioned. So spikes, lines, curves, sharp edges. This was all in that sort of domain. But as you can imagine, right, you're fighting this uphill battle because you have this huge pixel space, right? And there's so many almost infinite combinations you could potentially imagine putting on this sensor domain. And so the challenge is, how do you pick the most extreme examples and sample this space such that when you train your network, it's consistent at the points you train. And then by leaving some in your holdout set, you show that you're able to interpolate between examples well. And so that's the name of the game. What is the extent that you define in your data set, right? And do you cover the space of what you will expect to likely see so that your system will adapt and perform well within that domain of the training data? So things that interpolate aspects of what you may have looked at, which exactly is to your point. So continuing that, right? Imagine we had put information about threads into that data set. Well, then if that was actually part of the training set, we would actually have been able to detect that as well, because clearly from the raw image, we could see the threads of the screw. But our model, that was not particularly in its domain, and so that didn't show up. Um, so yeah.
So you've got this one project focused on dexterity. Do you think of collaboration as a separate area of research, or does dexterity lead you to collaboration in some way?
That's a fantastic question. Dexterity leads us to collaboration. So, a lot of the other projects in my lab are asking that question, and many of them involve manipulation of different varieties. So, we have a project in our lab that's working to say, well, what if someone lost their entire arm? They have a shoulder disarticulation, and you want to give them back a high degree of dexterity and therefore independence, right? What could you do? So, a lot of kind of solutions out there are body powered prostheses. And you have low degree of freedom manipulation to achieve that. And with that, people who use it can do incredible things. If you look at some of the videos, absolutely incredible things, but it's still not the same, right? If I asked you to do something that was extremely dexterous or tight, it would be very difficult. And even if it was possible to complete it, it may take you a lot of time if you're unable to, have the tools to accomplish that. So the question we want to ask is, how can we bring robotic autonomy and intelligence combined with human intent to have a robotic prosthesis such that the human is able to indicate to the robot what they want to accomplish. And if the human's input, be it from a gaze tracker or surface electromyography or brain computer interfaces, if these are too low dimensional to control every degree of freedom of a very articulated arm, which could be like 22 degrees of freedom if you think of all the joints, including the ones in the finger, that can be a huge cognitive load if you're having to learn how to use the system. Can I take an underactuated input? So the input from the human is much smaller than the number of dimensions of the states you must control to actually do a very complex task. Because I understand the task that needs to be completed, I could do it if it was just robotic autonomy, but now I'm trying to give the person agency. So how do I let them prescribe what I should do, let them feel like they're in control, and then handle the hard stuff because I know what their intent is?
Sounds like another job for machine learning.
Yes, it is.
So have you mentioned brain computer interfaces? Is that something that your lab is working with, something like Neuralink or one of the other platforms?
So we recently got into this space, and we're exploring sensors like EEG. So these are like the surface ones that are non-invasive. We have collaborators in the neuroscience department who actually have tons of more experience than we do in this space, and access to people who could immediately benefit from this work as it evolves. But I think something that we uniquely bring to the table is realizing the power of mixed reality. So, a human wants to give a robot an understanding of what they want to do. You want to extract this human intent, and maybe the robot needs to communicate to the person what it intends. This is a very complex thing to do, and as you know, like natural language processing has made huge advances. I mean, you have like ChatGPT and all of these models. We're getting really good at using natural language to talk with machines and to get useful information from machines. But as we've kind of discussed here today, computer vision is a huge tool. If you can take this from any domain, from autonomous vehicles to drones to robots, if you put a camera on something, machine learning has a lot of power that it can pull out of that. And humans, we rely on our vision as one of our key senses, right, in our everyday tasks. So mixed reality, particularly for me, augmented reality, which consists of wearing a headset that has a sort of visor in front that's able to project items into your field of view. And for some models, like the HoloLens, can actually see where you're looking, can provide a lot of useful information. And so, what we're excited about is saying, well, to date, one of the key challenges in these sort of brain computer interfaces to do these highly dexterous tasks, both for prosthesis or even for helping people who are, for instance, recovering from a stroke, is how do you understand what the human is intending to do when they think a particular thought? And traditionally, this really relies on them trying to move their motor functions and trying to correlate that because you know what that should happen, what that should look like. But again, that works really well if you're able bodied. But if you're missing your arm and I say, move your right arm, and you haven't done that in years, that's a really complicated thing to achieve. So, if I give you this sort of augmented reality headset, can I show you what I want you to do and ask you to think it and then learn using the image of what I asked you to do versus my understanding of what you commanded? And I can project those as two separate things, what I requested, and from what I detect, passing it through my model, what you commanded. And then the person through mixed reality can see this disparity and take action on it. And I, as the model, can then learn to approximate their outputs more efficiently. And so I'm
What is the action that the human is taking?
So usually this is thinking a particular thought. So if you were to say move your right arm, for instance, there's the motor cortex area that would fire in that regime, and this would produce a particular EEG signal that you could then detect and say, oh, they're trying to move in this particular way. Now the problem is this is a very noisy signal, right? And then there's also a windowing function, so it's not even instantaneous, right? So this is back to the perception question. How do you treat the brain as an observation space? This is kind of like you're taking an image of someone's brain, if you will, through these readings. How do you take that raw image that you have and interpret these signals? So the name of the game in the field for years now has been command sort of simple things where you know what the signal should kind of look like and perform that mapping. But the more complex these tasks become, the more this quickly moves out of the domain of what's currently possible. And if you kind of look at the literature, to my knowledge, the highest number of degrees of freedom that someone has been able to control is about 6 or 7. That's really low compared to a 22 degree of freedom arm you may want to ultimately, manipulate. And so if you have that windowing function, that signal, how can you take that raw signal and map it to the output that you want? And what's really exciting with this space is, this sort of sequential signal you have has an analog itself to language, right? Which means machine learning tools like transformers might become really useful again, right, in interpreting those signals. And this is kind of where the cutting edge research in this space also currently is. And if you can bring in vision and mixed reality to that, I think the future is extremely bright in that domain.
You mentioned that you're kind of pulling these signals. You're conveying them to the robotic arm, the intelligent arm, let's say, the intelligent prosthesis. It does something not quite what the human wanted, and then the human can correct it. Like, how is the human correcting it?
Right. So this as a first piece, right? Uh, we realize that it may be useful to start off with an augmented reality prosthetic to begin with. So if I'm, for instance, trying to command a task, and even in our very preliminary work, you don't even have to do a full arm. You can say, imagine just trying to move a point, right? So if I'm telling you to command a particular point location, which ultimately may be show me where you want your hand to go, how can you give the person a desired output? So I'm telling you, I'd like you to do this thing, move the point along this axis. And so I know what the person is trying to do because I told them to do it. Right. But then, their output may not completely match what I think it's saying. And so there could be divergence there. But if I'm making the assumption that they're doing what I'm asking correctly and reliably, then I just have to adjust my model. This is model uncertainty to approximate what I've been asking them to do.
Yeah, I'm not sure if this is a useful analogy, but it kind of makes me think of like some combination of like simulation and like in the context of Chat GPT, like we're talking about RL with human feedback a lot, and it's like human feedback in the simulated environment. We think simulations and these kind of visual environments. We think about reinforcement learning quite a bit. Are those tools that RL, for example, is that something that comes to play in your work?
Absolutely. So I have another student who's working again with this sort of mixed reality kind of paradigm, and we're applying it to two domains. One is how can you watch humans perform a task? For us, it's a packing task. How do we pack items into boxes? And there's a whole aspect of reorienting their shape to then place them in a tight fit. How can robots watch what a human is doing and extract that information about how they repositioned an object multiple grasps to do that? And then this other aspect too, which is very interesting, is well, if you want to efficiently learn a demonstration, perhaps with some human input, how do you ask the human an efficient question, right? How do you provide a human query? So there is strict RL in terms of just adapting, and as you mentioned, right? Anytime RL is explore and exploit. So you do something and you accumulate some reward, and then you change what you're thinking about the world to accomplish that. But sometimes exploring can be dangerous. If I have a moving robot, and it just explores and is driving around and it explores and it causes a collision, that may not be what you really wanted to do. So if you have a human there that can provide input, and this becomes the inverse reinforcement learning, or the human from demonstration version of this, if the rewards do not currently exist in a way that I can extract them easily, then I might need to pull them from the human. And if I need to pull them from the human, how can I do so efficiently? And so one aspect my lab is really excited about is thinking again, how can mixed reality, which is that vision component and providing information to the human about what the robot is thinking, having the person label uh, projected information from the robot so that the robot can learn more efficiently is something we're very excited about. So a very simple example is imagine you're reaching out to grab something and the robot's not sure about how it should actually achieve it. And so it realizes, possibly through model ensembles, that there's uncertainty if it does something in a particular way. And it goes, I need help. So what I'm going to do is I'm going to project this trajectory without actually doing it to the human, and they'll be able to see it through their mixed reality headset. And I'll ask you to tell me, is that okay or not? Right? And based on that feedback, I can actually learn and update my internal models in the spaces where I'm uncertain. And so a very interesting paradigm would be using this sort of uncertainty to determine when you should ask a question, and leveraging mixed reality to ask that question efficiently.
Yeah, what I find interesting about your work in this area and this conversation is that maybe more so than you know other times I've thought about it, like I'm really getting the picture of a prosthesis as a collaborator as opposed to an a tool. And that kind of calls into question all of the the work that folks like you are doing, and even the stuff that folks are doing with like industrial collaboration, collaborative robots, where you've got these independent you know mechanical computational things working with humans. There are all kinds of dynamics that come into play, and opportunities when you think about this thing as a collaborator as opposed to an appendage.
Absolutely. And I think the biggest challenge as we kind of move into this space, right? If you have a capable robot, is how does it think about how to collaborate effectively? And what that usually boils down to is having really good models of your teammates' behavior. So if you kind of think about, trust, if you're playing a basketball game, if we're playing a basketball game together and you see incredible plays, by some NBA teams, for instance, where they don't even look at each other when they pass the ball, right? Or when they float it up, they don't even need to look. And they know that the other guy or girl will be able to fly over and dunk, based on the setup that they've played, or soccer or any sport that you choose. It's because they've played together for a really long time. And by playing together for a really long time, they build these internal models of how their teammates are able to behave and what their teammates are able to do. And they have an agreed objective of scoring the point. So, with an agreed objective, and knowledge of what your teammate can do, you can actually predict how they would respond if you think forward in time based on how you may interact with them, and leverage that prediction to be a more effective teammate. You can push your teammate to the bounds and limits of their abilities by floating the ball up for the dunk because you know they're capable of achieving it. And so the that's one aspect that deals with trust. So it's the agreed objective and known control model of your teammate.
Well, and interestingly, like it is bi-directional, right? That the arm in this case needs to have a model for what the human is capable of. The human needs to have an internal mental model for the what the arm is capable of, and there needs to be kind of this mutual trust that I don't. Well, I may have to think about the trust in the arm to the human direction, but the human certainly needs to trust that the arm is gonna do what it's wanting it to do, and I think ultimately you want the human to kind of forget that the arm is a collaborator and it's just there helping it do what it's trying to do.
Absolutely, absolutely. That's definitely the goal. And I think you bring up a good point in that bidirectionality, and I totally agree. And the question is, how do you build that trust on either side, right? So for the human, right, it's the explainability, right? How do you make yourself more predictable? If you think about self-driving cars, right, you don't want to remove blinking indicators if you're going to change a lane, because that's a really good way to understand intent. And if you drive around, a lot of these kind of vehicles, self-driving vehicles, maybe over time you realize what they're capable of and kind of even the mistakes that they may make. And we do this even for people. If you're driving and you see a bus or a truck, we know that there's certain etiquette on how to drive around these vehicles because they have particular blind spots. So we have internal models on their behavior, and we know that we agree on the objective that we shouldn't crash. And so the last piece of that puzzle is the safety component. So if I'm driving around this truck or this bus, right, and I have this idea of their model, perhaps the most important thing beyond their agreed objective and their controlling ability is, what do they perceive? What is their perception? Do they see me? Do they see other things in the environment? If I have a model that may also, by the way, may need to be a machine learning model itself, that can model their perception as well as a model that can model their decision making given what they perceived, then I can do usually a really good job of fully predicting their behavior. And you have both safety and collaboration in almost any scenario you could imagine. And so this is work that I'm very excited about. Yeah.
How do you see the in these two fields we've talked about, dexterity and collaboration? How do you see that um, evolving kind of broadly in the field, over the next few years? Like beyond the work that you're doing, what are some of the other kind of big things that folks are tackling? And, are we in a phase where we've got all these things happening outside with you mentioned LLMs, chat GPT, like is that going to have a huge impact? Or are we in a phase of development where things are happening very quickly, or are we in a kind of head down and grind it out phase where we're trying to push the ball, just kind of push the ball a little bit forward?
I would have to say that the field of robotics robotics evolves extremely quickly, right? All the archive papers and everything, in the course of a year, there will be a new player, right, that has profound impact in the field. And that could be from models to hardware, right, across the domain, on the order of about a year and sometimes 2 years. Pandemic slowed things down. You see a huge step in a particular direction. I'm very hopeful that robotics will continue to take these big steps, but I think it's also important to think about what's guiding us, right? What are the big problems that we kind of see? Like in the pandemic, it became very important to be able to provide remote care, right? And then you have this aging world population where even in 2007 there's a paper that talked about how there was like a 1 to 3 matching between people who could provide service and the number of elderly people who needed that care. And that's just in America. And then you have the baby boomers and the worldwide community living longer due to technology, which is fantastic. But what happens when they need care, right? Do you move into a care facility? Are there enough people to do that? Right? There's a need, right? There's a need. There's a need in caretaking. There's a need in industry. There's a need in the kind of tasks that I mentioned, collaboration and exoskeletons, and even kind of having these systems that can exist around you. There's the need. And I think the need to solve the problems that are dull, dirty, and dangerous, right, are what drive roboticists to these solutions. And I think the need has never been more clear as it is now. And I'm very excited that that will continue to push us forward at a very quick rate.
Awesome. Awesome. Well, Monroe, it's been a true pleasure to speak with you, and I appreciate you coming on the show to share with us a bit about what you're working on.
My pleasure. This has been a lot of fun.
Thanks so much.